Hello, we're going to continue to work on this internal loading example. Remember, in the previous video, I have promised you we're going to look at both left and right section. And our goal is to make a cut here and find out what's internal loading at C, right? And what we have done last time is we look at the right section. So today our goal is to look at the left section and see if we get the same answer for the internal loading. So what we're going to do is we're going to draw our FBD of the left section, so which is AC segment, and here is where we cut, right? So that's A and C. So we're going to have this distributed load starts at 270 and gonna reduce to some point here. And remember from the last video we showed using proportionality or similar triangle, we got this value here. I believe it's 180 Newton per meter. So now, any other forces acting on this segment? Yes. So we need to find our reaction support at A, right? So we need to go back to the original FBD to find out the reaction at A and at A. So we have AX and AY. And since it's a fixed support, we're going to have a moment. And if we assume the moment is going to be counterclockwise, this is MA, we need to solve all the three unknowns. So what we're going to do is going ahead to solve them. So immediately from forces at X direction, you know AX will be equal to 0. Then let's look at forces at Y. We'll have AY going upward, and going down is this entire distributed load, and that's half. Base is 9, and distributed load density height is 270. Okay, so that will give us, I'm putting my calculator here, I have 1215 Newton. Okay, so AY, going back to this forces at Y direction, AY going up, and then you have negative 1215 Newton, that equals 0. Okay, then we can solve AY being 1215 Newton. The last thing to solve from FBD number 1 is this moment at A due to a fixed support. So where do we choose to do moment about? We can do A, then AX, AY will not show up in the equation. So what do we have here? We'll have only this moment, since we assume it's going to be counterclockwise, so that will be MA, positive. And they have distributed load 1215, and where is that located, right? So this distributed load is going to be located 1/3 of this triangle, so that will be actually I'm erasing that. So this is going to be actually exactly at this point C, correct? That's going to be 1/3 of 9, so that'd be 3 meters. So we're going to times 3. That's clockwise rotation, so that would be negative. That equals 0. That will give us the moment A, that is 3645 Newton meter. Okay, so once we have that, we're going to go back to our FBD number 2 here, which is our left section. Since we copied down the distributed load, and the only thing left is getting AX, AY, and MA back, So AX is equal to 0. AY is going to be 12, 15. And we also have this moment, 3645 Newton meter. Okay, so any other forces we needed to add to this FBD number 2? Yes, there are. Because we're solving what? We're solving internal loading at C. So we need to put our internal loadings back in here. So based on our sign convention, this is the left section. So tension, we're going to make it normal. So make it normal have to be tension. So that be going to the right to make a tension. So that's our N. And shear, we're going to make this entire section to clockwise rotation. So that's have to going downward. That's going to be our V. And bending, don't forget a smile. So make a smile on this side. So that's going to be our M. So we're solving our N and V and M. Hopefully we get the same answer as we did in the last video using the right section. Okay, so how do we solve that? We're going to using our our equilibrium equation. So forces at X. So the only forces at X is N, normal force, that's equal to 0. Okay, now forces at Y. We have this 12, 15 going upward. And then we also have this shear force going downward. That equals 0. Oh, I'm missing, right? There's not only just, I forgot the distributed load, so I'm gonna go back. So our distributed load is going downward too. This is interesting because this distributed load is what shape? Is this trapezoid shape? So it's gonna be a triangle on the top of a rectangle to find out the entire area, right? So we needed to go ahead and solve that. So that's going to be if you add the triangle, it's going downward, so it's negative. Triangle is half base. A to C is 3 meter, so times 3. And what's the height here? Height here, that will be our 270 minus 180. So that's our triangle area. Then we're going to minus our rectangle area, which will be 3 meter times 180. Okay, all that's going to be equal to 0. Now let's take a look. Solving V. So V will be equal to 12, 15 minus half third times 90 minus 3 times 180, that's give us 540. And let's continue to solve that. This is 45. So 12, 15 minus 135 minus 540. Okay, so I'm putting my calculator. That will give us the answer of 540. That happened to be the same answer you have in the last video, correct? Okay, so that's our V. And that's our N. So last thing we need to solve is this moment. Well, this is a good time to review. How do we solve the moment? Where do we do moment about? That's right, where we cut. So we're going to do moment at this point where we cut. So based on this FBD number 2, for this equation, what's included? So we have this 3645 right here. So that's going to be counterclockwise. So that's positive. That's moment itself. Then we have this 1215. That's a force. We're going to times the moment of arm, which is 3. And that make it clockwise rotation. So that's negative. Then we don't forget our distributed load, right? So first we're going to look at this triangle, which we have done earlier. It's a half, 3, times height. Height is this value times 90. That's just the magnitude. And where is this located? This is located 1/3 from A. So it's 1 meter. So which is 2 meter to C, to where we cut. So we're going to times 2. And that gives counterclockwise rotation, correct? So this is actually plus. Now we're going to look at this rectangle down here. Rectangle, the area is 3 times 180, like what we did earlier. And where is this located? Right at the centroid, 1.5 from C. So we're going to times 1.5. And that make it counterclockwise as well. So that will be positive. Okay. So move on. The last thing we left is N and V. N and V going through the point where we cut. And so that's 0. And then you are solving this M. And this M is what rotation? It's counterclockwise. So that's going to be plus your M equal to 0. Okay. So knowing that, we can go ahead, solve it. Solve our M. So continue. So we have 3645 minus, that's giving us what? 3645 for this term. And then we're going to plus 2 and 2 canceled. So it will be 270. Then plus of here. And what's the value here? So I'm putting my calculator. So 180 times 4.5. That gives us 810. Then plus M. That equal to 0. And those two cancel out. That would give us M to be equal to negative 1080 Newton meter. You got the same answer, right? So if you compare with the previous video, and you got exactly the same internal loading, all three of them. Normal force, check. Shear, check. Bending, check. They're all the same. So now let's recap. Which one is easier? Using the right section or left section? So obviously for this problem, the right section is way easier. Why? Because first reason, when you use right section, we do not need to find reaction support. No need to find reaction support at A. That saves one entire step here. The second reason, since the distributed load is just a triangle versus what we have here in the left section, we have this trapezoid shape, and then you have to decompose to two of them, two shapes, triangle and the rectangle. That is another added steps here. So, however, I do want to show you either section will give you the correct answer. And it's good to try both at the beginning and just get comfortable with this steps and scales. All right, hopefully you enjoyed it and have a good time. See you next time.